Smithsonian, the WMAP satellite has produced results that have defined our standard cosmology. The main person who has led the data analysis and the cosmological interpretation of the results was Professor David Spergel, one of the most respected cosmologists in the world. If you have written papers on cosmology, chances are you have referenced David's WMAP papers, which are among the most cited papers in physics and astronomy since 2000. So it's my great pleasure to introduce him today. Professor Spergel got his PhD from Harvard University in 1985, was then a long-term member at the Institute for Advanced Study, and since 1987, he has been a faculty in the Department of Astrophysical Sciences at Princeton University. In addition to CMB, David has worked on a wide variety of topics, ranging from the nature of dark matter, novel ways of detecting planets orbiting other stars, and satellite missions that will reveal the nature of dark energy that's driving the accelerating expansion of the universe. And to recognize his work, he has been awarded numerous awards and fellowships, including the MacArthur Genius Fellowship, the Goover Prize, and the Shaw Prize. Currently, he chairs the National Academy of Science Space Study Board and co-chairs the NASA Science Definition Team for the WFIRST Space Telescope. Today, David will share with us his view of the current status and the future directions of CMB, Planck, and beyond. Let's go.
Thanks. Some nice feedback. So what I want to do today is give my view of the current state of cosmology, focusing really on microwave background cosmology. I'm giving another talk on Wednesday here to the astronomers, and that's going to focus much more on gravitational waves and the search for gravitational waves. That I'll get to talk a little bit about at the end of the talk when I get to looking at the future and looking at where we're going. But most of what I want to say about gravitational waves will be on Wednesday. Next Wednesday, week from tomorrow, 8 days from now. You know, when I originally gave the title for this talk, I had thought that the Planck team was going to have released their final data release, which was scheduled for sometime in 2014. And they were committed to ESA to release it by 2014. Things are, as we all know, everything's harder than you think it will be, and everything takes longer, and they have not released that data yet. So what we're going to do in this talk is bring you up to that release. And there'll be a whole bunch of issues that I bring up that are kind of open questions on where we go next. And what should be fun is I anticipate a bunch of the things I will talk about will be resolved by the end of the month when we have some more data. The fact that that's true may be one of the things that, for those of you far outside of cosmology, should be one of the takeaways from this. Cosmology is in the midst of an incredibly exciting time where the data keeps improving significantly year to year, and that the results we have from satellite and ground-based experiments are improving at a very rapid rate. And we've seen this with temperature, and now in measurements, and now we're in the midst of this with polarization. So what I want to do is sort of say where I felt we were after the 9 years of WMAP data, what we had learned. And to summarize that, I think after WMAP, we have pretty well established that there was the standard cosmological model, a model with 6 basic parameters: the age of the universe, the density of atoms, the density of matter, the amplitude of fluctuations and how they vary with scale, together with what we call the optical depth, which measures what's the probability of the microwave photons getting from redshift of 1100 to us, and is sensitive to when the first stars form. With those 6 numbers, you could fit not only all the data from the microwave background, but measurements of large-scale structure and supernovae, and we are in a situation where all the pieces fit. And, and on one hand, it's a very simple model. It's 6 parameters. It says the total energy of the universe is 0. The Euclidean physics we learned in middle school is valid on the scale of the universe. The fluctuations that we see in the microwave sky are Gaussian random phase. We look at 1 million separate points in the sky with WMAP. Planck, you're looking at 10 million separate points in the sky. The statistical properties of all those 10 million points can be characterized fundamentally by 2 numbers. It's a Gaussian random field characterized entirely by a 2-point function, no higher moments. That 2-point function comes from a power spectrum that can be fit by just an amplitude and a slope. So you can go from 10 million numbers to 2. The universe couldn't be simpler. That said, it's a model, and we'll talk about this through the talk, where there's some enormous open questions. Atoms make up less than 5% of the density of the universe. Most of the universe is in the form of dark matter and dark energy. I'll be giving a talk in 10 days at Academia Sinica, the physics group, talking about dark matter and dark energy, so I'll advertise that one. The plan is, though I don't anticipate people going to all of them, there are actually 3 separate talks, so if you're interested, you can hear all of them. When I was in Paris for a year, I gave the same talk 10 times in Paris and no one noticed. Institute to institute. Then the other big questions, and this ties into the search for gravitational waves, is what generate these fluctuations? How did the universe begin? And I'm not going to talk a lot about this today, but we have this, on one hand, we have this idea of inflation that serves as an interesting mechanism for generating fluctuations and explaining large-scale structure. It's very beautiful and elegant in some ways, but it contains a lot of contradictions within it. All right, so now let me get into the story and just remind you of the basic cosmological model. So in the basic hot Big Bang picture, the universe starts out very hot and dense, and as it expands, it cools. And as it expands, it gets less dense. So as the universe expands, and this is plotted in terms of redshift, there's a pointer here. Yeah, but everyone can see the word redshift. I can point it. These days, with people tweeting, I was at some talk, and I'm sitting there in the back, and someone in front of me is tweeting, I can't believe the speaker's hand is so shaky. It's so distracting when someone does this in the talk. So I'm not going to use this as often as I'm So redshift is telling us about how the universe is expanding. Redshift of 1,000 means that characteristic distance between galaxies is 1,000 times smaller. The density of the universe is 10 to the 9 times higher. So as we go, redshift goes, time goes this way, redshift increases that way. So as we go back in time, the universe gets hotter and denser. Around a redshift of 1100, the universe makes the transition from being ionized to being neutral. It's very close to when it makes the transition from being radiation-dominated to matter-dominated. And in terms of physics, the fact that these two are close seems to be, in a sense, just a coincidence, in that the physics that determines the baryon to photon ratio and the physics that determines the dark matter abundance comes from 2 kind of different sectors in the models we have. That sometimes stuff just happens, perhaps, or maybe there's something more profound there. This transition from ionized to neutral occurs really rapidly. You'd think So naively you'd say, well, temperature of the microwave background today is 3 Kelvin. It's about a few times characteristic energy, about 10 to the minus 4 eV. The binding energy of hydrogen is 13.6 eV. This transition should have happened, at about a factor of 40 higher in redshift, about 40,000. That's when the typical photon was able to ionize hydrogen. The reason why the transition takes place so late is that we live in a universe that has a lot of entropy. There's over 1 billion photons for every atom in the universe. That means that when you look at the Planck distribution, the photons that are ionizing hydrogen are way out in the tail of the Planck distribution. So when you're here, and you've got to be 30 e-folds out in order to ionize things, there's still e to the 10 photons available for every hydrogen to ionize. And when you get here, and you're at 40 e-folds out, only then do you start to make the transition. And it doesn't take very long to go between 40 e-folds out and 44 e-folds out. And e to the minus 44 is a lot smaller than e to the minus 40. So you very quickly go from being able to keep the universe ionized to the universe being neutral. The fact that you have that very rapid transition gives you a very well-defined surface to velocity scatter. So almost all of the photons we see in the microwave sky, that we'll talk about, all the fluctuations we see, the fluctuations reflect the physical conditions right here. And in this early time here, you can think of the photons and dark matter as being very tightly coupled, so that variations in density generate sound waves that produce the pattern we see in the microwave sky. And most of what we see basically reflects the physics of those sound waves. So you've got density fluctuations, they set off sound waves, the sound waves ripple out, you've got an outgoing ripple. You take the Fourier transform of something that looks like a ring, and that gives you, in Fourier space, this pattern here. And the lines look brighter on my screen, but the theory line goes right through the data, and this is just the Fourier transform of a ring. It's the acoustic fluctuation propagating out. And the fluctuations are damped on small scales by a process called silk damping. And that's because you've got this plasma of electrons and photons. The photons, I said, are tightly coupled early on to the electron and photon. But around the time of this transition from ionized to neutral, the photons become less well coupled. And when that happens, the heat can diffuse. So that diffusion damps the fluctuations. And that's why the amplitude of fluctuations drop with scale. And this showed the data. This is after 5 years of WMAP data. We'll see it improve. But already here, there's very clear evidence for detailed measurements of the acoustic peaks. And here's some measurements on smaller scales by Akbar and Boomerang and CBI, some of the ground-based experiments showing the balloon-based for Boomerang, that you were getting a consistent fit of small scales. And from this, we could fit this basic model. 5 fundamental parameters, and then when the universe formed. And we fit that model, it fits the data really well. And in many ways, I think of that as taking the universe's baby picture. We've measured what our physical conditions 380,000 years after the Big Bang. And this is a picture of 3 randomly selected babies shown 3 days after they were born. And then if you know the initial conditions, you can run them forward in time and predict what they'll be like today. Having had 3 kids and raised them, it doesn't work with children. But remarkably, the early universe, it works pretty well. And what we do is we go from the initial conditions forward in time. And this is a picture I grabbed, but to show how things evolve, this child is now taller than the other two in the middle. So, you know, it's not a fully accurate picture of redshift 0. So this is what we do. We take, let's see if this animation works. There we go. Our initial conditions. We run them forward in time. We start with fluctuations in the initial conditions base that we see in the microwave background. We run them forward on the computer, basically just using gravity at the level of these simulations here. And what we see is the emergence of structures and, you know, the kinds of, you know, we see these rich clusters, the kind of things that Yen-Ting studies in his work. And what we do is we compare what we see in the universe today in the structure of these clusters and the large-scale distribution of galaxies to what we observe. And the broad picture is it fits remarkably well. And this is a nice plot that René Lozic made a couple years ago that looked at the amplitude of fluctuations versus mass. And what you see here is over a range of 10 to the 10, we've probed the mass fluctuations, going from an amplitude of about a part in 10 to the 5 on the largest scale to the quasi-linear range here. And the brown points come from measurements in the microwave background, where we're measuring this amplitude at redshift of 1100. The blue points are from the Sloan Digital Sky Survey looking at galaxies. And these yellow and green points are from measurements of clusters. And these points from the gas clouds, Lyman Alpha Forest. And the curve here is our basic lambda CDM model, which for the point of view of fitting this, has two parameters. The amplitude of fluctuations, and what sets this break is when did that transition occur between radiation domination and matter domination? When was that transition at redshift 2000 translates to a physical scale. That's the break in the spectrum. And with those parameters, we fit all the data. So, you know, where I felt we were was 2 years ago. We had this, 3 years ago, we had this simple model. Basically general relativity in the uniform universe. Flat universe with the odd thing of this strange composition, or not knowing what the dark matter and dark energy is. And the pieces fit, most importantly, with other observations. There are lots of different ways we have of measuring these basic cosmological parameters, besides the ones we get from the microwave background. Measuring distances to supernovae, measurements of the Hubble constant. You know, I'm old enough to remember when going to conferences when people argued whether the Hubble constant was 50 or 100. Now we argue whether it's 67 or 72. But, you know, right now, all these basic pieces, properties of clusters, a very important one for me in terms of testing the standard model is cosmological abundances. Deuterium is a cosmic fossil. Most of the deuterium in the universe was created in the first few minutes of the Big Bang. And the abundance of deuterium depends directly on the baryon-photon ratio. The ratio of the first to second peaks in the microwave background also depends directly on the baryon-photon ratio. They depend on the same number. And the two measurements agree within their errors, 5%, on what the baryon-to-photon ratio is. I find this really reassuring because the deuterium abundance depends on nuclear physics and the physical conditions 3 minutes after the Big Bang. The height of the acoustic peaks depends on how electrons and photons diffuse relative to each other and physical conditions 300,000 years after the Big Bang. The fact we get the same answer from two very different techniques is really reassuring. So where do we go from here? We want to go and test the model. And I'm going to focus first on temperature measurements and the effort to go to smaller and smaller scales. So with WMAP was a big step when we went beyond Kobe mapping the whole sky at the degree scale. to WMAP with a characteristic scale of about 0.2 to 0.3 degrees, to Planck, where you get to about 0.1 degree. And I'll talk some about measurements from experiments like ACT and SPT where we get to smaller scales. And the way I think about this is we have a model, and the model makes predictions. This is where we were after this plot, I think, is now 7 years of WMAP data before we started getting ACT data. And we had some measurements on small scales, but we hadn't really filled in this picture here. And you can see silk damping and the finite thickness of the cell size of that shell for the acoustic fluctuations make very definite predictions on what we should see. And I'm part of one of the big collaborations called, as Yenting worked with this as well, called the Atacama Cosmology Telescope. And this is a telescope in Chile on the border with Bolivia and Peru in the Atacama Desert. It's very high and very dry. Astronomers like to go to high, dry places. Some this isn't high and dry enough, so they go to the South Pole. This is easier to get to. This is a picture of our telescope viewed from Google Maps. The telescope's surrounded by a ground shield. So it's the only way you can get a good picture of the telescope at this point, now that the ground shield's there, is looking down. So there we are looking down on the telescope. It's quite impressive on Google Maps, at least. You type in your home address, and you can see, I know from my house, I can see on Google Maps the number of skylights I have. And I can see the skylight over my bathroom from Google Maps. As Yenting mentioned, I've been working on the WFIRST project. And that involves taking a 2.4 meter telescope that was transferred from the National Reconnaissance Organization to NASA. So they transferred it for one of two reasons. Well, first they transferred it because they wanted to make sure it get used. It was actually quite a good thing. They wanted to make sure it didn't go to waste. But the fact that they had this available meant either they were done with spying from space, possible. I don't have any classified knowledge, and if I did, I couldn't say. I don't. I have no clues. Or they have something bigger. So they have even better pictures. So this shows where we were pre-Planck. Here's the WMAP measurements. Here's measurements from the South Pole Telescope. These points are independent. These are actually correlated. That's why there's more of them. But the key thing here is that they fit the model. Mostly, you'll notice things lie above the model. And that's because this does not include the effect of gravitational lensing. This is what the fluctuations looked like when they left that surface of last scatter at redshift of 1100. When you include the effect of lensing, and I'm sorry this line is too faint, this faint line here is a theoretical model out here, and that goes right through the data.
Is this a data or the simulation?
This is data.
All data.
This is all data. So the data looks just like the theory. And we fit the data. This is actually fitting things here and running them there.
What is the dashed line?
The dashed line is if you don't include gravitational lensing. So the next step is Planck. Planck went up and mapped the whole sky at 9 frequencies, higher sensitivity and resolution than WMAP. And the impressive thing to me is we see very consistent stories. So this is taking the Planck data and smoothing it to the WMAP resolution. And WMAP Planck has finer scale features here, but actually looking at this figure, we are limited not by the resolution of the experiments, but the resolution of that projector. It's actually higher resolution on my retina screen. But you can see the same picture. There was some issue that the amplitude difference between, you can't, even though these are plotted at the published values, this amplitude of fluctuation is about 1.2% higher than this plot, the relative polarization. And one of the things that the Planck team has, they haven't published but announced at the Paris meeting in December, is they've redone their calibrations. And now now the calibrations agree with EDAs, so that we see at this level very consistent story. Now, this picture isn't what we measure directly. What's measured directly looks like this. So these are the Planck observations at 9 frequencies, going from 30 gigahertz up to close to 900 gigahertz. And what you see is, in addition to the microwave background photons, the stuff over here, you see this very bright emission in the middle of the picture. Let's see. Where did I put the... Oh, there's where I put it. Okay. This is our galaxy. This is plotted in a coordinate system where this is the galactic north and south poles, and this is the plane of our galaxy. And at these low frequencies, you're dominated by emission from synchrotron emission from relativistic electrons moving in our galaxy. Here we're dominated from emission from thermal dust. And there are several different components that contribute as we move across in frequency. There's significant contribution from free emission from ionized gas in our galaxy here. Emission from spinning dust grains in addition to thermal dust emission becomes important here. And when we look at these clean maps, what's done is people take linear combinations of these different maps. We know the spectrum of the C and B quite well. We fit for the spectrum of the different foregrounds with more data than parameters. You can do a pretty reasonable job of removing the foregrounds. That said, when we do our cosmological analyses and look at, we actually always compute the statistical properties of this piece of the map and this piece of the map, check it with the bigger picture, but we don't tend to make use of this region here, because in order to get there, you have to remove this stuff here. And you don't want to be sensitive to the details of whether you remove the galactic foregrounds accurately enough. This is actually, I think, a better representation of what's going on in the Planck map, is every little patch here, you actually have measurements like this. So you're actually looking at, measurements with a resolution of about 0.1 degrees when you're looking at the Planck map of the sky. And not only do we get good agreement between the space-based measurements, but when you look now at the ground, and here's measurements from Planck at 143 gigahertz, same patch of the sky from ACT at 148, here's ACT and here's Planck. ACT has better angular resolution than Planck. Its angular resolution is about 5 times that of Planck and has lower noise, but it's not looking at the whole sky. Planck has data on the whole sky. ACT are looking at small patches, now growing patches. I could show similar plots with the South Pole Telescope, or on larger scales with experiments like BICEP and Polar Bear. They all agree remarkably well. I mean, right now it's, I think, a tremendous success that all these different experiments using very different techniques, different times detectors, all see the same thing on the sky. And you have to keep in mind that these are fluctuations at the level of millionths of a degree. And here,